Welcome to our seminar today on air management and system pressurization in hydronic systems. You will find this is a subject we need to spend more time on because there are two keys to making sure you get a good running, highly efficient hydronic system. In today's seminar, we're going to touch base on system pressurization and air control. And we start looking at components. We're talking about the components pretty much in this slide. You're looking at an air separator, roll air troll, that helps control where the air is separated out of the system. On the top of that, you're looking at a air vent and a pressure reducing valve for controlling the minimum pressurization of the system. In addition to that, you will see a bladder tank. And a bladder tank, as you may note in this particular slide, is at the same level as a roll air troll and not above it. It's at the same level. That's one of the advantages of a air removal system, as we'll talk about as we go. So we're going to go through each of these components today, talk about what they do, how they work, and how they're critical to making sure you have a good, modern, high-efficient system working for you. So we got to start at the beginning. The beginning would be open versus closed systems, and trying to understand real quickly the difference in the two. And probably the best way to do that is to kind of give you a little history lesson here. At one time, all heating and cooling systems were open to the atmosphere. This is a typical example of an old boiler system with some radiators. And the point is, we have the expansion tank at the high point. It's an open tank. It has to be at the high point in an open system. And you have to have makeup water going to it. And it's open to the atmosphere, and all kinds of stuff could collect in that open expansion tank. The point being, they'd have to be at the very high point of the system, being open, otherwise the water would just fall right out of it. That would be a problem. So what could happen in these old open systems? You've got fresh water coming in, you've got oxygen coming in, you're going to get corrosion. You're going to get oxygen, iron, rust, you're going to create all kinds of problems. So little picture we've added here are some examples, as horrible as it might sound, of stuff we have found in open expansion tanks on top of buildings. Yes, I'm sorry to tell you, we found birds and bats and cans and all kinds of stuff in it, which is not a very pleasant thing. But the point being, again, is an open system is going to corrode. Why would we show a Coke can here? And I think if you start thinking about open versus closed systems, this is a great place to begin to think about what the difference would be. When you buy a Coke can or a bottled drink somewhere, it's under pressure. It's in a can or in a bottle under pressure. And that particular beverage would last a long, long time until you pop the top. So in essence, a Coke, before you open it, is a closed system. It will last indefinitely. You can keep it for a month, for 2 months, for a year. I don't know how long you want to go, but the message is, as long as it's under pressure, no fresh water, fresh oxygen going into it, the Coke is still good. So it's a closed system. As soon as I pop the top to the Coke, I have an open system. And when I get an open system, how long would you keep that around before you would consume it? Obviously, if you're sitting here in a seminar, you probably have a beverage of some kind. It will be great for the next hour, but it won't be good for very, very long after that. I think we kind of got the message. So let's look real quickly at a closed system. Now, what have I done now? My expansion tank is now closed. It's under pressure. It is sealed up with mechanical seals, manual air vents. No way for fresh water to be leaking from it, no way to bring in oxygen. And I've seen closed systems 10, 15 years old that the water is very clear inside, that the piping inside is clean, because when you close it up and seal it off properly, you start with some air, but air is 80% nitrogen. So that original air charge has 20% oxygen, roughly 80% nitrogen. And yes, that oxygen is going to go to iron oxide fairly quick inside that closed system. But if you don't add any more oxygen, what's left? What's left is nitrogen. Now, nitrogen is an inert gas. So now you've got a closed system. The only thing really in it gas-wise is nitrogen, which is inert. How long will that last? It'll last forever. And it really, really will if you keep them closed. So obviously what we want to do whenever we can is design systems closed so we don't have a continuous stream of fresh water going in. And it might be helpful to give you some examples in the world we work in of what would be open versus a closed system. Certainly chilled water should be a closed system. Certainly hot water heating should be a closed system. Most of the time, when you start looking at condensate pumps to steam systems, the condensate pumps would be an open system. Therefore, you're using Schedule 80 pipe, normally condensate return lines as an example. Your plumbing systems would be open systems because the water goes through one time, we use it, and we go to drain with it. So that's an open system. Cooling towers, condenser water, would normally be an open system with an open type of a cooling tower. So we're going to be focused today on closed systems, air control, and system pressurization on modern chilled water, modern hot water heating systems. That's where we're going to focus our time. Now, when you look at this, how can you make sure you have a truly closed system? Now, here we have a bladder tank or what we think is a closed system. We designed it properly. We have it under pressure of 12 pounds. We got 4 pounds at the top. How could this be an open system? If you got a leak in this kind of a system, and you got a leaking piece of pipe somewhere or water falling out, and you got a bladder tank, the bladder tank will maintain its charge because it's sealed off. It doesn't lose its charge. But you got makeup valve there, 12 pounds, bringing in fresh water to replace the water that you lost in your leak. What comes with the replacement water? Oxygen. What's the oxygen going to do with iron? It's going to rust. So you no longer have a closed system. You now have an open system, and you got fresh water coming in. So when you use these air elimination systems with bladder tanks, how do we know if you have a leak? One possibility, if you look ahead a little bit and you look at ASHRAE, what they talk about is, this is from the ASHRAE handbook, and what they're warning you is that with these automatic makeup valves, maybe we want to monitor any makeup water. In other words, there should not be makeup water going into the system. It should be just enough pressure on that pressure reducing valve to maintain the pressure. So if we got a lot of water going in, there's a leak somewhere, and we got oxygen, we should have an alarm that we should know about. So ASHRAE really, in this kind of a situation, would probably recommend to you that we put a flow meter in there, flow switch, maybe even a water meter itself to measure or be aware. Are we bringing makeup water into what we thought was a closed system, making it open? I'm getting a little older, and I've seen weird things in my life, and one example would be we actually found a system where the janitorial service was taking the water out of the boiler directly to clean floors because it was hot. It's convenient. They were not doing anything but just cleaning, mopping floors, not hurting anything. But they didn't understand that taking water out of the boiler for a mop bucket made it an open system. Simple little thing. And a little flow meter here would have warned everybody that's what was going on. So those are the kind of things that can happen to you if you don't keep that in mind. So let's look a little bit at expansion tanks. What are expansion tanks? Why do we need them? What types are out there? Well, Bell & Gossett makes a whole bunch of different types of tanks. The first one we're going to look at is a plain steel tank. It's ASME. It's a steel tank. It's been around for a long, long time. And actually, the sizes can get bigger than this, but these are probably the practical standard sizes. We also have a Series D diaphragm type tank. Again, this would be a pre-charged diaphragm from the factory 12 pounds, but we pre-charge these so we cannot lose the air charge. The difference in the two is in the plain steel tank, the water is in contact with the air. The water is in direct contact with the air. There's no membrane. The Series D diaphragm tanks, and as we've seen on the next slide, the bladder tanks, the water is actually protected from the air by a membrane. In other words, you have a membrane that we pre-charge with air, so the water is not directly in contact with the air in the expansion tank. It is in contact with the air in the system, and we're trying to control the system air, but it's not in contact inside of the expansion tank with the air, because that's a bladder there, like a big football bladder, that we pre-charge to make sure we have an air cushion. So that's the major difference. And the Series B is the full bladder type of tank, and we'll talk about them more later on, where we can actually get full acceptance volume of the tank. In other words, if we had a 53-gallon tank, we could start off with 53 gallons of air in the cushion. That would be the acceptance volume available. So we'll take a little bit closer look at these as we go, and we're going to talk about them and why we need them. Here's another picture of a standard expansion tank, steel tank, water in contact with the air. The way we did it for years and years and years worked quite well. Today's marketplace, I would suspect this is probably 10% of the market or less, and the diaphragm bladder type tanks are probably 90% plus of what we see. But you're going to see these, particularly on older jobs. You need at least to understand they work and how they work. First of all, if you have an old type standard steel expansion tank or compression tank with water in contact with the air, a lot of the old timers wanted sight glasses on the side. And one straightforward statement to you would be to please valve off the top sight glass so the cork or the material or gasket material doesn't get dry, because it's a source of leaks. And just note and think about this. If this is under pressure and you get a leak at the top sight glass, your tank's going to become waterlogged. It's a very common problem, but I think you see what's going on here. If we had a leak at that top sight glass and the system's under pressure, air is going to leak out and the water's going to fill up in that expansion tank until we get a waterlogged tank. Also, in the old-fashioned or the way we were brought up, standard tanks, water in contact with the air, we used air-troll tank fittings. And this is a typical one that we have used before, called ATF. This prevents gravity circulation between the tank and the system. It also helps establish the correct water level when you start the system up cold. Real quick comment would be, it keeps the water temperature in the tank at ambient temperature, and your water in the boiler could be 160 to 180. So that kind of gives you the reason for doing this. It, in essence, gives you a smaller tank because of the air-troll tank fitting. It helps you start it up and get all the air out to begin with and have the proper water charge inside your tank. I think one other side comment here you should recognize in a regular tank. This tank is not full of air at startup. Once you get it started and get the pressures on it, it's going to be partially full of water depending upon the makeup pressure when you start it off. In other words, the acceptance volume in this tank is not going to be 100%. It's going to have some portion of it full of water when you start the expansion process. In other words, you fill your system up with water. The tank is sitting at 0 psig when you start it off, and you start adding water in it, so you got an air cushion, but that air cushion is going to be under pressure. It's going to compress somewhat, and you don't have a tank that's 100% acceptance volume. That's why bladder tanks, properly charged, can physically be smaller. One other quick comment on this. This air-troll tank feeding needs to be above the air separator so we can have the air moving back and forth by gravity, by just rising air. So here's some pictures again of the pressurized bladder tanks. The one on the left would be a full bladder. You can replace it. You can have 100% acceptance volume of air in the bladder tank if you have it properly recharged when you start off. The diaphragm tank on the right, you cannot replace the bladders. It just has small tanks inside it. It's a throwaway tank. So why do closed systems need an expansion tank? Very simple. You heat up water, it's going to grow. You also need a point of no pressure change for the pump. We're going to examine these two things because they're two real good reasons that you need expansion tanks, and you need to understand them when you apply them and when you troubleshoot. Because if you got the wrong size tank, you're going to have problems. And if you don't have it in the right location, you're going to have system pressure problems. So let's take a quick look and make sure you kind of understand where we're headed. Basically, if I take 2,000 gallons of water at 40 degrees and I heat it up to 180 degrees, I've got 56 gallons of water I got to do something with. Water is non-compressible. You heat it up, it's going to get bigger. And when it gets bigger, it's going to go somewhere. So you've got to have an expansion tank or some place to put the 56 gallons of water, or you're going to have a major problem. So this is why we have to size them accordingly. So where are we going to put this 56 gallons of water that grew from the 2000? So let's take a quick look and make sure you understand the system pressurization piece too. So the first piece is we got that water we got to put somewhere. Now how about the location of this expansion tank? We preach it pretty much should be on the suction side. Why? We like to reference ASHRAE as much as we can. So here's the ASHRAE handbook. You can go check this out if you like. Wouldn't hurt if you would go read this section and make sure you got it in your head. But real simple, let's look at a pump and let's look at the location of the tank and what happens to the pressures on the suction and discharge of the tank when we turn the pump on and turn the pump off. On the top drawing, let's call it drawing A, the expansion tank's on the suction side and we're pumping away from it. And with the pump off in the 8th drawing, obviously the discharge gauge and suction gauge on the pump are both reading 30 pounds. Now when we turn the pump on, if the pump's doing 10 pounds of pressure boost about 23 feet ahead, notice the suction side stayed at 30 pounds because that's where the tank is. And the discharge pressure went up to 40 pounds. So when the expansion tank is on the suction side, we are increasing the pressure on the discharge side of the pump when we're turning on. We're adding pressure to a system. Let's go to example B, next set of drawings, and it shows again with a pump off and the expansion tank on the discharge side of the pump, 30 pound suction pressure, 30 pound discharge pressure. But when we turn that pump on, doing 10 pounds worth of work, and we're pumping into the expansion tank at 30 pounds, we don't change that number, and your suction pressure drops to 20 pounds. So the expansion tank, per ASHRAE, per Bell & Gossett, is the point of no pressure change. And we're going to look a little deeper at that on the next slide. But the key thing you need to understand is we did not change the pressure inside the expansion tank when we turned the pump on and off. We changed the suction pressure, we changed the discharge pressure based on the location of the pump. So if we kind of get that message as we went through this and you see the differences of what happens as I cycle my pump, 40 pounds on the discharge or 30 pounds on the discharge based on the tank location. Why is that possible? Let's take a quick look. This is a closed system. I've got a pump pumping away from the expansion tank. I got the tank pressurized at 12 pounds. I got my system at 12 pounds. What can add water to the tank? There's really only two ways that we can add water to that tank. And adding water to that tank is really the only way that we're going to change the pressure. If we heated the water up or had a thermal expansion of the water, then we could force some water into the expansion tank. We could raise the pressure. Or if we had makeup water, we came along with a makeup valve and changed the pressure from 12 to 20 pounds, we'd add water, that would increase the pressure. But cycling the pump is the key question, if you don't understand. If we turn the pump on and off, do we add water to the expansion tank? Just turning the pump on and off, and the answer is no, we do not. So if we know that, then we can locate the expansion tank as a point of no pressure change and use that to control system pressure throughout our whole system. And most of us don't stop long enough to understand how important it is to control system pressure. And this is what this whole point is all about. So let's go a little bit further. If we're pumping away from the tank, which is normally the way we recommend, always pump away. Few exceptions would be high-rise buildings or when you're worried about system pressure getting too high. But 99% of the time, we're going to be pumping away from the point of no pressure change, away from the expansion tank. And when we do that, if our fill pressure is 12 pounds, if that T where the expansion tank hooks into the closed system is 12 pounds, if that T is close to the suction side of the pump, then when I turn that pump on and off, I can't change the 12 pounds. The only way to change that 12 pounds is to put water into the tank or take water out, and turning the pump on and off is not going to add any water to the tank or take any water out. So what happens? If the tank's on the suction side of the pump is close to the suction of the pump and it's 12 pounds, when I turn the pump on, it's going to stay 12 pounds. So the pressure goes up to 26 pounds on the discharge by whatever the head whatever the work that the pump can do will be added to the 12, and I wound up with 26 pounds, and as I go through the friction loss all over around my piping system, I lose that back down to 12 pounds again at the T. So pumping away from the tank really makes good sense. If you're pumping towards the tank, what happens? Now all I've done is put the pumping into the T now. T is on the discharge side of the pump to the expansion tank, real close. It's at 12 pounds, and I think you've learned by now I cannot raise that 12 pounds. I cannot change the pressure at the point of no pressure change. Therefore, the suction pressure, hard to believe by some people, drops. Therefore, the suction pressure drops by the amount of pressure work that the pump is doing. In this case, it drops to a negative 2 pounds. Isn't that amazing? Drops to a negative 2 pounds. Discharge stays at 12. And if you're pumping 200-degree water, ladies and gentlemen, you might have a big problem here. Therefore, we don't normally do this. This is usually not the way that you want to pump. You normally want to pump away. In this particular case, if you had air problems, you just made them horrible. So you put an air vent on the suction side of this pump, and what do? You suck air in. It just won't work. So we try always pump away 99% of the time. So here's another little example of where a lot of times we would see the air separator and the expansion tank at the top of a high-rise building. This is, say, an 8, 9-story building. And the pump's in the basement. The reason we would do that, that makes the expansion tank smaller. You know, the field pressure controls the tank size, so it's at the high point will be smaller. This is okay as long as you understand the pressure seat. So I'm 90 feet up, so when the pump's not running, the pump's seeing 39 pounds of pressure. 2.31 feet makes a pound of pressure. So the pump off, just the static pressure of 90 feet of static pressure of water puts on my pump 39 pounds of pressure plus the 4 pounds of pressure I'm going to have on my field pressure to give me 4 pounds at the top. In other words, I'm going to have my pressure reducing valve set for 4 pounds makeup minimum to make sure at the top of my system I got 4 plus that 39 pound elevation. So the actual pressure on the discharge of my pump and suction of my pump with the pump off is 43 pounds. 39 pounds plus the 4, and the pump's not running. What happens when I turn the pump on? What happens to the 43 pounds on the discharge? What happens on the 43 pounds on the suction? And my pump hits 140 feet, divided by 2.31 feet makes a pound. And look what happens. Next slide, I kind of just turn the pump on, and tall building example, and what do you wind up with? You wind up with a suction pressure dropping from 43 down to 13, 30-pound drop. And you see the discharge pressure going up from 43 pounds to 73 pounds, a 30-pound increase. Assuming the pump is exactly halfway between the high point friction-wise, you get a 30-pound rise on the suction, on the discharge, and a 30-pound drop on the suction, which may be fine. 13 pounds, this would probably work okay, as long as you understand system pressures are being controlled by the expansion tank. The system pressures, which are critical to controlling air and having a very happy system, are being controlled by the expansion tank and its location. That's the point I want you to understand. Nothing wrong with this, as long as everybody can accept that. Let's take a little bit further with tall building examples and pressure reducing valve locations. This 4 pounds at the high point is desirable to have a slightly positive pressure with the pump off. And by doing that, we can get most of the air out. So this pressure reducing valve location becomes pretty important. What you really want to do is control the pressure at the point of no pressure change. You want to control the pressure of the expansion tank. And you do that if you locate the PRV where the T connection is, or where at the same elevation, at the same location where the expansion tank hooks into the system on the suction side of the pump, which in theory should be the lowest pressure at that elevation of the expansion tank. So now you can kind of dial in whatever makeup pressure you want minimum. So it's on a location, it makes sense. If you get below 12 pounds, it's just going to start makeup water. It's going to maintain that minimum pressure on your air control system of 12 pounds. Now, we've seen some jobs where people try to put them on the discharge. They work fine on the discharge as long as the pump's off. You got to stop and think about that. It would work fine if the pump's off, but you're not going to run a system with the pump off. So as soon as my pump comes on, the pressure goes up because we're pumping away from the point of no pressure change. We're pumping away from the expansion tank, so the pressure's got to go up. So if the pressure goes up, how's the 12 pounds going to work? It won't. The pressure reducing valve cannot maintain the minimum pressure, and this is not the location for the makeup line. You want the makeup to be at the point of no pressure change, where the expansion tank hooks into the system would be the ideal location for it. So as we work our way through some of these, here's a typical example of what would happen with the pump we just showed you before. The suction pressure is 12. We turn the pump on. Discharge pressure jumps up when the pump's on to 26 pounds. And as we can see, the pressure reducing valve is not going to work too well in this location. So let's talk a little bit about expansion tanks. How big should they be? How big a tank do you need? Now, obviously, going back to our example of expansion, water is incompressible. I've got 56 gallons of water I've got to do something with. And hopefully we put it in the expansion tank. That's what the goal would be. Remember, the expansion tank has two reasons to be there. One, it controls system pressurization that we just talked about. Put pressure through the whole system so we know what it is and we can maintain it. The second one is, where do we put the extra water? Where do we expand the water? Those are two key reasons you have the expansion tank. So with a 56 gallon of water, let's just pick a typical tank. We had 56 gallons of water being expanded. So we just took a quickie look. Would an 80 gallon tank, an 80 gallon acceptance volume, a B300, would that be big enough? It's a good question. Would it be big enough? So let's just kind of ask that question. We need to store 56 gallons of water somewhere, the acceptance volume. Will this B300 tank be big enough? So here we go. I got 2,000 gallons of water at 40. It's going to become 2,056 gallons of water at 180. With an 80 gallon B300 bladder tank to be big enough. What is our fill pressure? Our fill pressure is 12 psig. So makeup pressure is 12. We got this closed system. We got a bladder tank. You just stuck an 80 gallon bladder tank on there. Is it big enough to hold the 56 gallons of water? Well, let's go to Charles and Boyle's law and take a look. Well, we got to have a place to put 56 gallons of water. Now we're going to start off with a tank that's 80 gallons of air if it's pre-charged. The nice thing about a bladder tank, if you pre-charge it to the makeup pressure, we can start the tank off with 100% air. We can start the tank off at 12 pounds gauge pressure if we pre-charge it to 12 pounds, so that when we first turn our system on at 40 degree water to makeup water, we got 80 gallons of air in our 80 gallon tank to work with. Great. Now what happens as we heat it up to 180? Well, and that 56 gallons of water is going to go all into an expansion tank. If you take the 80 minus the 56, that leaves 24 gallons of air. Remember, there's a bladder in here separating the air from the water. There's a membrane or bladder separating air from the water. We pre-charged that bladder to 12 and had 80 gallons, and now we put 56 gallons of water into it and compress the 24 gallons of water. That's quite possible, but the pressure's got to go up, right? So how much would the pressure go up? Well, you know, we all go back to high school chemistry and physics, to old Boyle's law. We have to use absolute pressures. So 12 psig is 27 pounds absolute. And we work through the absolute pressure ratios here, we wind up with the pressure V2, pressure P2 of being 75 pound gauge pressure. We started with 12 pounds with 80 gallons of air. We wound up with 24 gallons of air in our closed system, in a little membrane, but the pressure now is 75 pounds. Is that okay? Well, it would be okay unless you used a boiler, like in this case, with a boiler with a 50-pound AS relief valve. So now what's going to happen? Your boiler's going to pop. As you start heating it up, the relief valve is going to pop. So it would not be big enough because the equipment we're trying to protect limits us to 50-pound AS relief valve. Now, not all boilers that way. Maybe we can put a bigger valve on this thing, but the point is, what is the weakest point in your system? That's the max pressure you can put on the expansion tank. So going back to this 50-pound relief valve will discharge, expansion tank is too small. Bottom line, the B300 is not big enough to take care of this problem because of the 50-pound ASM relief valve limitation. So what do? Well, we work our way through some other tank sizes, and we started with the B300. And as you can see, if we went to the next size tank with 106 gallons of acceptance volume, that we wound up with a final tank pressure of 43 pounds. The B500 would also work. It's a bigger tank. The final tank pressure, when we put 56 gallons of water into it, would be 32 pounds. The B400LA and the B500LA, their acceptance volume is too small and they will not work. So a B400 would be okay, or B500 would be okay. A B300 would be okay if we had an ASM relief valve with a pressure higher than 75 pounds, it would be fine. So we could look at the equipment maybe and work at it. So probably would specify the B400 if you have a boiler with a limitation of 50-pound relief valve. That would be the tank size proper for this case. So what is the symptom of an undersized expansion tank? How would you know your tank's too small? Well, I hope you guys understand some of this. Let's look at sizing tanks and some information available for you. We'll put them all up here real quick and I'll run through them. You need to have a good set of software tools for sizing expansion tanks. She'll walk you through this. And Bell & Gossett has an ESP Plus system that's free, it's online, and does a fantastic job of visualizing what we're doing and walking our way through it. In fact, I've got a screenshot coming up that we'll take a look at. I'll kind of keep in mind the higher in the building you put the tank, the lower the pressure will be on the tank. So remember you got Boyle's law you're working with, so the smaller the tank. Remember the higher the relief valve setting you can put on there, the smaller the tank. Remember we're working with Boyle's pressure ratios. So the higher the max pressure we can have is that relief valve pressure. So the higher the relief valve pressure you have, the smaller the tank. We would recommend decreasing the max pressure from the expansion tank about 5% below the relief valve pressure. In other words, if I had a 100-pound relief valve in my system, I wouldn't want to take the system pressure any higher and say about 95 pounds. These valves are going to start weeping a little bit before you get there, and you want to give them a little bit of safety room, 4 or 5 pounds, so about 5% when you go sizing expansion tanks. Bladder tanks, if they're pre-charged properly, will physically be smaller than regular compression tanks. They're going to cost more money because they've got a bladder. Standard plain steel tank, water in contact with the air, has no bladder, costs less money, but it's going to physically be bigger, and it's going to have to be mounted above the air separator, where a bladder tank can be mounted on the floor horizontal to it. Another little tricky piece, we've always recommended that on chill water systems, use 100 gallons as a field pressure. As your temperature. Use 100 gallons as your max temperature. And you say, well, that's chill water. Yeah, but using 100 gallons, you'll get a tank on most systems 15, 20 gallons, no big deal. The other piece is, how many times is it possible for a large system to lose power? If you lose power on a hot August day, the water in that 45-degree water is going to start warming up. Will it ever get to 100 degrees? I doubt it, but you want some little safety factor there. And if you've got a big system, you might bring the system down a little bit, like a university system that's huge. You might drop the 100-degree water down a little bit. But remember, what is the max temperature you ever expect in that system? And you also want to make sure you've got an expansion tank big enough to be the boss, to be the point of no pressure change. Also keep in mind, glycol expands at a different rate than water, and you need to take that in consideration when sizing tanks. So here's this screenshot of ESP Plus, and it really is a freebie. You can go online and get it. It really, really helps. This is the air removal system. But take a quick look. If you come in here and just check off what you're trying to do, like a commercial system, and you want to use a diaphragm bladder tank, great. It just walks you through it. What's your inlet temperature? What is your max temperature? What's your field pressure? Yeah, you've got to tell us what the field pressure to give you 4 pounds at the high point. What is the max working pressure in the tank? That's going to be limited by the ASM relief valve setting. How much to come into the system volume? How many gallons of water? We don't know. You're going to have to estimate that. If you want a quickie estimate, we have, if you click down deeper, you'll find a method to help you estimate the amount of water that's in your system. So we got to have the gallons, and then we got to have the fluid. If it's plain water, fine. If it's glycol, you can go a little bit deeper in that screen, and it'll give you the percent glycol. It'll help you come up with bottom line to hit size tank, and you've got yourself a nice little detail of what you're doing. It walks you through it. You're really going to love this, and I really would strongly advise you getting familiar with this and using it for selecting your tanks. Get a screenshot, keep it for your files, and you know what you did. So what can we do to fix a system where the expansion tank is too small? If it's a bladder or diaphragm tank, we should immediately check the pre-charge pressure. As you're going to see in a minute, we ship them from the factory at 12 pounds, and we need to make sure it's pre-charged to the makeup pressure to make sure we take full advantage of that bladder. So first thing is, did somebody pre-charge the tank? Unfortunately, a lot of times they don't get changed. They go in at 12 and then they get too small simply because we didn't put the proper air charge at the time of startup on the system. If we could decrease the fill pressure, now we got 12 pounds, let's say they give me 4 pounds at the high point. If we could lower that number, it will make the tank more effective. Change out the relief valve. We showed the boiler a little while ago where the ASME bladder tank at B300 was too small, but that was because the boiler relief valve was 50 pounds. Maybe the boiler's rated for 75 pounds. Maybe the boiler's rated for 125 pounds. Maybe the manufacturer of that boiler will let us just change the relief valve, and it's fine. And you ought to check that, because a lot of times it's just that simple. A lot of times we get a low pressure ASME relief valve on a boiler, and that same boiler is okay for 100 pounds. We just have to put a high relief valve on it, and now our tank works great. Move the tank to the high point. I don't think we're going to do that a lot, but tank at the high point has lower fill pressures, it sees lower pressures, and therefore it's going to be much more effective. Add another tank. We can always put another tank in parallel. The B300 there is not big enough. You can always put another tank in parallel. They work fine in parallel as long as you got one connection to the system at the point of no pressure change. There's no reason you can't do that. Change out the tank to a bigger tank. In our case, go from the B300 to the B400. More expensive, but we'll certainly take care of it. And we'll be happy to help you walk through this anytime you have a problem. Give James and Pleasance a call. Our guys and our people all understand air control expansion and the air control system to maintain the right pressure, so don't hesitate to give us a quick call. Will air in the system cause problems? Ashley says yes. That if you get air in the system, you're going to get noise, you're going to lose stability of the system, you're going to lose heating and cooling ability. So noise comes from high velocity. You got air in train, it's going to be noisy. And it's going to, you can hear that little bubbles being pumped around the system per ASHRAE. So we definitely want to control the air. We definitely want to try to get the air out of the system if we can to avoid problems. Notice this particular situation, I've got a heating coil or a cooling coil that's air bound. And the pump's on. How do I know the pump's on? Because the supply main water column is higher than the return main water column. See the difference in the two? So we know the pump's on, but there's air up there, and the air is trapped. So we have no flow through the heating coil and or the cooling coil here. No flow means no heat. No flow means no cooling. That's bad, all because of air. So let's look at the point of no pressure change and what happens if we get air out in the closed system. Now, real quick at this slide, you've seen it before. We got an expansion tank. We got 12 pounds pumping away from the expansion tank. We got great system pressure control. But look over to the right. What would happen if these little round football-shaped things are air bubbles out in the system? They're air-bound coils out in the system, just like the one I just showed you in a previous slide. How does the pump know which one is the boss? How does the pump know where the point of no pressure change is? We don't know what's going to happen. You start getting air out of the heating coils, the cooling coils, they might behave like an expansion tank. The pump's stupid. It doesn't know where you intended for the point of no pressure change to be. It's back in the expansion tank, but it doesn't know that if you put air bubbles out in your system. So that's really a bad thing to have happen. Here's a primary, secondary, variable volume system with a variable speed drive on it, a chill water system, great system. We put it in to be very efficient, lower that pump speed down, save all that energy, and we let air pockets get into the cooling coils, look at that center cooling coil. It's got an air pocket at the top of it, okay? We got a two-way valve on it. What does that mean? Stop and think a little bit. An air pocket is going to cost you money by your pump running faster. Wow. Air pocket's going to cost you money by your pump running faster. Absolutely. You got air in that cooling coil, in that center coil. That means if you got air in a water cooling coil, it's not going to work too well. The heat transfer is not there. So nobody's happy because you're not getting cold air off the coil. You got flow through the coil on the bottom of the coil, but the whole top of your coil is full of air. So you got flow through the coil, but the top of the coil is full of air. It's not working right. So what happens? The thermostat in the room on the wall says, I'm not happy, and tells the two-way valve to do what? Open, wide open. Now you got a two-way valve wide open on that center cooling coil to try to put more water through it, but the air in the cooling coil doesn't let it work properly, but now you've got more flow. Now your pump's got to run faster to give you more flow, even though you're not getting any cooling out of it, and you wind up with an energy hog. So getting air out of a system is critical to making sure you got an efficiently running system. It's very hard for some people to see this connection, and I hope you understand with this slide how important it is to get air out of those coils and get it back where it belongs to make your systems run at the minimum energy levels we can get them to run. So let's look at air control system. I hope by now you realize we took care of the system pressurization. Let's look at air control. Two basic types of air control system. One would be the air control system where the standard expansion tank, and this is where the water and the air is touching each other in the expansion tank. The compression expansion tank has to be above the air separator so we can move by gravity back and forth. The air can move back and forth, and the tank has to be above the tank. This is the system where I would say 5 to 10% of the volume out there. You're going to see these primarily on older projects. They work great. So you got a makeup valve, pressure reducing valve, you got an expansion tank, you got a roll air trough, you're pumping away from the system, and you want the hottest water you can get in there. In this case, we got the boiler water going into the air separator, and that's an air control system. How about the air elimination system? In the air elimination system, we're going to be using a bladder tank. And you might note here, now the bladder tank can be at the same elevation as the air separator. The bladder tank does not have to be above the air separator. In these older systems, one of the biggest problems was we might have a 500-gallon tank up in the air above the roll air trough, and how do you structurally put it up there? Nice thing about a bladder tank is they're physically smaller, and you can just sit them right beside the air separator on the floor. They're going to be on the floor of the equipment room, no big deal. We're going to eliminate the air through a high-capacity automatic air vent. See, the air separator here has the high-capacity automatic air vent on the very top of the air separator. So any air that we wring out of this water gets dumped into the air separator, gets dumped into the high capacity automatic air vent, and we get rid of it. We got a pressure reducing valve, makeup valve there to control the pressure. Point of no pressure change. The bladder tank is just hooked right in on between the pump and the air separator. Great air elimination system. And for the record, the water in the tank is not in contact with the air in the tank. We have it under pressure. We pressurize the bladder tank. Therefore, it runs quite well, but make sure you understand that this is a great system, and it's probably 90–95% of new projects are going this way. So a little fine note would be try to avoid putting the bladder tank directly under the pipe or directly over the pipe. We don't want trash plugging anything up, and we don't want to have an air pocket trapped there. So that's kind of the reasons for that. So pipe air vent discharge to drain, the 107A, the vent from that should go to drain to get it down the drain so you don't get a wet floor if it starts leaking on you a little bit. And here's a little picture of that. The float actuator, they're high capacity air vents, they're heavy duty, rugged cast iron, and you want to pipe these things to a drain somewhere in case you get a little water coming out with the air. So there are two types of pressurized tanks. I think we talked about them earlier. And again, this is the bladder, where the air is in the bladder pressurized. The bladder tank, the bladder can be taken out and replaced. The diaphragm tanks are throwaway, you cannot. That's the difference in the bladder and the diaphragm, about that simple. And we ship them from the factory at 12 pounds. Remember, we're going to have to pre-charge these tanks on the job site to the makeup pressure at that elevation to make sure when we start off, they're 100% full of air. So here's a little pre-charged example of a pressurized tank, and just get your numbers real quick. What pre-charge pressure would I want my bladder tank to be if my makeup pressure is 30 pounds? I got a pressure reducing valve coming in at 30 pounds. That 30 pounds, by the way, should be the setup to give me 4 pounds at the highest point in my system with the pump off. That's how we come up with the 30, and we'll talk about that in a few minutes. But again, my bladder tank's at the same elevation as my makeup valves, at the same elevation as my air separator. What pre-charge pressure do I want on my bladder tank? And what I'm after is, think about it, I'm after making sure when I turn the system on, my bladder tank starts off with 100% air. So basically, I've got to get that bladder tank pre-charged to the 30 pounds. In other words, I got a makeup valve pressure of 30. If before I hook the tank to the system, I go ahead and pre-charge that bladder to 30, then at startup, the bladder will be 30% full of air, be full of air with 30 pounds of pressure on it, and my makeup pressure would be 30. I'll have my tank 100% full of air cushion at startup. I've got 100% acceptance volume available to you for the expansion of the water. That's why the pre-charge is so critical. In this case, it should be 30 pounds. No water enters the pressurization tank during system fill. If we do that, we can get the whole volume. We want to make sure that you get in your head to pre-charge those tanks before you hook them up to the system. And one last comment, if you don't do this, you can have problems. What are the symptoms if your tank hasn't been properly charged? In other words, you got the tank from the factory, in this particular case, at 12 pounds, and you did not pre-charge to 30. What's going to happen if your tank's going to be too small? You're probably going to pop your ASME relief valve. Your relief valve's probably going to start popping. So let's try to see if we can understand some of this. So basically, how can we verify that the tank has the right charge? How can you check it after the tank's installed? We are strongly recommending that everybody standardize this little TPV tank purge valve. This purge valve goes between the bladder tank and the system. And all it is a method that you can isolate the bladder tank to check the pressure on it. In other words, the little drain allows you to drain the expansion tank. The valve side of this fitting goes to the system. The other side goes to the tank. So we could actually valve off system pressure, and we could drain the water out of the tank, the little valve at the bottom. We could also put a pressure gauge on there and check the pressure. So now we can also pre-charge the tank, and we can check the charge on the tank, even if the tank's still connected to the system. This should be standard on every detail out there. Every engineer in the world should put these things because it makes life easier. And if you get a problem with understanding what your pre-charge is, or you've got a bladder tank problem, this helps you with it tremendously. So it should be kind of mandatory every time you use a bladder tank. So how about air in solution? What do we know about air? The hotter the water, the less air it can hold. You know what a deaerator does for a living? You know, a deaerator for a living, basically you heat the water up to drive air off. So if you cool water down, you suck air in. So hotter the water, the less air it can hold. The cooler the water, the more air it can hold. You kind of got to understand these basic things that you already know. The lower the pressure of the water, the lower the air pressure on the water, the less air it can hold. The more pressure we put on water, the more air you can drive into it. So these are kind of fundamental things about air you already know. If you take a glass of water out of the faucet that's been under pressure, and you kind of sit on your desk, let it just sit there and kind of warm up, you would normally see little bubbles forming around the water coming up to the top because you've taken the pressure off. When you take pressure off, the water had a bunch of air in it under pressure. You take the pressure off, air starts popping out. So these are the rules we want to understand. So if you're taking pressure off of the water, is that cold water, that water is 60 to 70 degrees, sits on your table, it warms up. So you're warming the water up, driving air off. You're taking the pressure off, driving air off. So what does that mean to you? The lower the pressure and warmer the water, the more air you get out of solution. So I wonder where the best place would be for an air separator. Well, wait a minute. You're telling me hot water and low pressure. You got it. that would be where you want your air separators to be. So the lowest pressure possible with the hottest water. So in a chill water system, we would normally put it with the return chill water. Return chill water would be 55, 56 degrees, which is probably the hottest point in the system. That's where we want the air separator. We also want it on the suction side of the pump. And most times, in this particular situation, primary, secondary, you've got that little green bridge in there, but we're on the suction side of the distribution pump, which is normally the high head pump. So the ideal location on a primary secondary system for the air separator would be, as shown here, hottest water, suction side of the primary pump. When possible, place the air separator in the warmest water. In this case, we got a boiler. Where's the hottest water? Obviously, the hottest water is coming off the boiler, so we would prefer to pump away from the boiler, away from the air separator, away from the expansion tank. That gives me the lowest pressure and the hottest water, and I got my best shot to get the air out of it on startup. I really do. That's very critical, you understand that. So when you have a system under pressure, when you pop the top, what happens? You lose pressure, air comes out, and you now have an open system. I think this, going back to this old Coke can, is a great way to illustrate to you the difference in an open and closed system. And what is our goal? Our goal is to always keep that closed system. We don't want an open system. So let's keep this in mind a little bit and have a little fun and understand some of this. And related to this would be the system pressurization. And when you take pressure off of water, air pops out. When you heat it up, air pops out. Now, what in the world could this have to do with the Thames Tunnel River? Thames River in London is where the first large tunnel was made under ground. And they actually, in 1843, tunneled down underneath the Thames River, which at this time London is probably one of the most active seaports in the entire world. The British Empire was probably controlling the world. This is London. And they put underneath the river now, in 1843, they dug a tunnel. You could walk through, as you can see pictures of it here. Trains could go through it under the river. When it was completed, they kind of considered it the eighth wonder of the world. Now, it was 75 feet below the water level of the river, the lowest water level of the river. This tunnel was 75 feet down below that, so the ships could pass back and forth above. And kind of keep that in mind with system pressurization. This is a little fun. So when they finished up the tunnel, all of London were just so excited about what they were calling the eighth wonder of the world, 1843. They put a big party in the tunnel, and they had champagne, and they had a great big party down there. And they were drinking champagne. They were 75 feet below the water of the river. The river's above this tunnel. They're in the tunnel down below the river. Atmospheric pressure is up. Not a whole lot, but a fair amount. You're down below enough that pressure is higher. They're all drinking champagne, all having a great time. And when they walked out of the tunnel, came up to the surface and rose up 100 feet or so in the air to get back on street level, guess what happened? Very simple. They all got intoxicated because the bubbles started coming back out. The champagne was full of bubbles. When it came to the roof, when it came to the surface of the streets of London, all those gas bubbles started coming out. And when it came out, people got sick, thought they had a problem. This is one of the first examples of understanding what happens with pressure on gas. Pressure driving air in solution, taking pressure off, air pops out. Kind of a trivial tidbit, but it's kind of interesting comment. So there are lots of bubbles, air bubbles in water that you can control by pressure. And it's another example of milky water would be water under pressure. And when you take it out of a faucet and you put it in glass, it looks milky because it's got so much air coming out of solution because you took the pressure off. So what can we do with this? Little thing you've learned about adding pressure to drive air in and taking pressure off to take air out. Which side of a cooling coil or heating coil would you put a circuit setter? Which side? And I'll show two different possibilities. I got my circuit setter on the left-hand side on the outlet, and on the right-hand side is on the inlet. Now remember, the worst place in the world to get air would be in the cooling coil. You don't want air in that coil. So by putting it on the supply side, let's take a quick look. If we leave the circuit setter on the outlet side in this case, keeps air out of the coil, because air removables from the system is very simple. So if I back up real quick, I want a circuit setter on the outlet side to keep the pressure in my cooling coil as high as possible to drive as much air in as I can. Therefore, all drawings that I've seen, all ASHRAE drawings I've seen, show the balancing valves on the outlet side of the coils, not on the inlet side. If they're on the inlet side, then we're reducing the pressure by the pressure drop through the balancing device, which lowers the pressure in the coil, which means air is going to pop out in the coil. If we put it on the outlet side, we keep the pressure higher in the coil, we drive air in solution there, and we can make it work much better. Therefore, we preach, everybody shows in their drawings, balancing devices belong on the outlet side of a coil, not on the inlet side. Air removal from systems, and there's a couple little tidbits here you might want to look at. If you go back to ASHRAE and Gil Carson, 1981, this is a trivial little thing, but worth looking at. If you can keep velocity above 2 feet per second, you can entrain air and take a vertical piece of pipe and take air down with you. If you get the velocity below half a foot per second in a piece of pipe or in any place, the entrained air is just going to pop out. So if you're building an air separator and that's all you've got going is you want to keep it below half foot per second. If you've got a coil above you and you're trying to bring air down, you want to size your pipe on above 2 feet per second to bring the air down with you. So take a little quick look at a system sizer based on pipe size. Scale 3 gives you that velocity. So when you start looking at some of these, you need to kind of be aware of those velocities if you're worried about moving air around in the system. So let's go back to the air-bound system we had earlier. Here again, the pump's off, and you see that we got air trapped in a coil. Now we said if we could size that pipe on 2 feet per second, we could take that air and bring it down. But the next thing is we got to make sure we get flow through the coil to entrain the air and bring it down to 2 feet per second. So the pump is off, air is trapped in a terminal. You see with the air coil, the water coil is 3 feet above the pipe, 3 feet above the pipe, and we've got air, what, 1.5 feet of air and 1.5 feet of water. When we turn the pump on, the pump raises the water on TA, lowers the water on TV, but we don't have enough pump pressure to force water through the cooling coil. So what do we got to do? If we added a circuit set on the return side and made sure the pressure drop of the circuit setter was higher than the elevation of the coil above the main supply main, then we could force some circulation. That's all we've done. We put a circuit setter on that piece of pipe with a 5-foot drop. That means I got to have more pump head now to make it flow, yes. But that extra pump head would allow me to get the water that much higher to the coil, and I can purge the air out of the cooling coil. Now, if I size my downcomers on 2 feet per second, now I've got a way to actually vent a coil at a high point by making sure the pressure drop through my circuit setter on the return side is higher than the elevation of my coil above my main pipe, above my supply main. That's critical, making sure you got more pressure drop through the circuit setter than the elevation, and we make sure we size it on 2 feet per second. We can actually take the air out of the coil. We can purge it right out. Nice little trick for some of you senior engineers listening to this. You may have never heard of this. It works. It works like a charm. You just got to spend a little bit of time sizing your pipe properly, and you may have to actually put a circuit setter in there and put a little extra pressure drop to make sure you get the water up that high. Cute little idea, and I really think it makes some sense. So if we start looking at velocity reduction air separators, the inline air separators, we got to be down to 6 inches per second to make sure the air comes out. We got to slow the water down. If we go to a roll air control type of device, we have tangential flow. So now we got centrifugal flow. Since it's centrifugal force, air being lighter than water, air comes to the middle. The water on the outside where the biggest force is, we're bringing the air right out of it, so it really does a wonderful job of taking air out of the water using centrifugal force. Here's a little picture of that where we ran some stuff in the lab, did some CAD analysis type approaches to it, and you see how they work. We get that high velocity around the edges there, we just wring the air right out. These things work. So when you specify an air separators, make sure you're looking for centrifugal connections. They really make a huge difference. Tangential connections where you get centrifugal force working for you. Here's some charts on the efficiency, but again, with tangential connections, we can control the efficiency and get up to 90% of the air out on the first pass. Of the entrained air, we can get over 90% of it out on one pass when we size them properly. So here's a little comparison between the inline air separators that do not have centrifugal force. You've got to get the velocity down to 0.5 foot per second versus air separators with tangential connections, spinning that water, centrifugal force, they can be smaller. So you see the capacity difference. So the message is, in your specifications, you should always demand tangential connections to make your air separators work much better. If not, and if it's just an inline kind of a tank, that inline tank has to be physically bigger to get it down to 0.5 foot per second to get the same air separation capability that a roll air control will give. So this example shows you a 30-inch tank being roll air control. This is good, 2,000 gallons per minute, where if you look at a 42-inch tank required for the inline type. It's hugely critical, real simple thing to add to your spec, making sure all your air separators come with tangential connections. Just that simple. It's not a very hard thing. And you might call this a boiler's best friend. We're seeing more and more buffer tanks. Now, by nature, buffer tanks a huge amount of water, and guess what? Very low velocity. So they really do make a great place as an air separator because we got the water down below 6 inches per second. You can put an automatic air vent, 107A air vent on top of these things, and they do a nice job of separating air. And then not the expansion tank. You still got to have that bladder tank or an or expansion tank somewhere, but they can take care of the air separation bit. And if you've got a huge buffer tank, chill water, hot water, and you're slowing the water down to below 6 inches or 0.5 foot per second, they work really well as an air separator. So here's a typical lock and wall buffer tank. You can even have tangential connections on them if you wanted to make it more efficient. This is not an expansion tank. Don't make that error. It will take care of the air separator. What is correct field pressure for a building? We talked earlier about 1 pound of pressure is 2.31 feet of head. And that's pretty much what we've been trying to teach. So if I had a column of water 2.31 feet high, vented at the top, the gauge on the bottom is going to read 1 pound. If it's 23 feet high, it's going to read 10 pounds. If it's 231 feet high, 23-story building, I've got to have 100 pounds of pressure, street level, just to get the water to the top of the building. And what we're going to preach to you is we want 4 pounds of pressure at the high point with the pump off. Our field pressure should give us 4 pounds at the highest piece of pipe in your system with the pump off. That way, with a manual vent, we can get the air out. Here's just a typical little example. If the building was 30 feet high, or if the highest piece of pipe was 30 feet elevation-wise above the field valve, what pressure would I need to make sure minimum I got 4 pounds at the high point? So basically all I'm doing is taking 30 feet divided by 2.31. I come up with 13 pounds elevation, and we're going to need to add 4 pounds to give me 4 pounds at the high point. In other words, if my pressure reducing valve pressure is set for 17 pounds, and I'm 30 feet below the high point with the pump off, if I set that PRV valve for 17 pounds, I'll have 4 pounds at the high point. I can open that manual air vent, get all the air out, and my system is full of water. We ask you to please put this field pressure on your drawings. With the pump not running, it's important that you specify that number because people sometimes just don't adjust. They don't know. So please write that number on your drawings. So note for temporary, if you've got a system that's higher than 230 degrees, which would be unusual to be honest with you, you might need a higher field pressure because of the vapor pressure of the liquid. In other words, you get above 212, you may need additional pressure just to make sure the water stays warm. That's a flash and steam. Thank you for listening to us. We've enjoyed it today. We've covered a lot of grounds. Please remember, controlling air in your system and getting rid of it is critical, along with system pressurization. When you follow these things we talked about, you'll have a trouble-free system. It's the most efficient system you can have in the world. It's a closed system for heating and or chill water when you size it properly. Thank you. Have a great day.